In the last session, we learned about refraction and why it happens. Refraction is bending of light. Light bends because its speed is different in different medium and because light is a wave. And the two laws of refraction are this. The incident ray, the refracted ray, and the normal at the point of incidence lie in the same plane. It's pretty much similar to the first law of reflection, but the second law of refraction is different. It says that the ratio of the sine of angle of incidence to the sine of the angle of refraction is a constant for the given pair of media. It is not that the angle of incidence is equal to the angle of refraction. That was the case in the second law of reflection, but not here. And this law is called Snell's law. So today, let's learn about refractive index and then also learn Snell's law more deeply. When a ray of light goes from one medium to the other, we will call medium 1 as the medium in which the light originates and the medium 2 into which it goes. Then N21 is called the refractive index of medium 2 with respect to medium 1. And this refractive index is a function of both the media. Suppose medium 1 is air or vacuum. So medium 2 is some other medium. Then N2 air is called the refractive index of that material with respect to air, and that is called absolute refractive index or simply N2. So it's like this. We have a medium 1, we have a medium 2. A ray of light comes like this, and let us say medium 2 is denser, so it bends towards the normal. So N21 is when the ray goes from 1 to 2. That is important. When you say N21, refractive index of medium 2 with respect to 1, we are saying that the ray is going from 1 to 2. That is basically the ratio of the speed of light in medium 1 divided by the speed of light in medium 2. So the speed of light is v1 here and v2 here. The speeds are different. That is why refraction is occurring. So N21 is v1 by v2. All right. Now, if this is air, then for air, this v1 will be c. The speed of light in air is nearly equal to the speed of light in vacuum, and that is called c, which is a universal constant. Then, in such a situation, when medium 1 is air, then N21 will be called simply N2, which is the refractive index of material 2, absolute refractive index of medium 2. That is speed of light in medium 1, that is c, divided by the speed of light in medium 2. Another medium N3, its refractive index N3 is c by v3, etc. So if you multiply N and v, N2V2 is equal to C, N3V3 is equal to C, that means NV is equal to constant. Absolute refractive index of a material multiplied by the speed of light in that material is a constant. So the absolute refractive index of glass, we write as N glass, is C divided by the speed of light in glass, that is V glass. And that has been measured to be 3 by 2. So therefore, V glass will be equal to 2 by 3 of C. C is equal to 3 into 10 to the power 8 meters per second. Speed of light in vacuum or air is that much, enormous speed. So speed of light in glass is 2/3 of this. That means 3 will cancel. 2 into 10 to the power 8 meters per second. The absolute refractive index of water is C by speed in water, and that has been measured to be 4 by 3. So therefore the speed in water is 3 by 4 of C, that is 2.25 into 10 to the power 8 meters per second. Light slows down as compared to air or vacuum. Light slows down when it enters any other medium, be it glass or water or glycerine or plastic or whatever transparent medium. It slows down as compared to air. But extent of slowing down is different. You can see in glass it slows down more than it slows down in water. In glass, the speed is lesser than in water. Now consider that a ray of light comes from water to glass. Okay, then what will happen? A ray of light goes from water to glass at an angle. So it will again bend towards the normal because the refractive index of glass with respect to water now. You see, N21 was ray going from 1 to 2. So NGW, glass water, is when the ray goes from water to glass. That N21 was V1 by V2. So in our case, this is 1 and this is 2. So V1 by V2 means V in water divided by V in glass. And this was 2.25 and this was 2. 10 to the power 8 was the same. So the ratio is 2.25 by 2 is equal to 1.125. Now, the meaning of a high refractive index means what? Compare glass and water. The refractive index of glass 3 by 2 is higher than the refractive index of water, right? What does that mean? You can compare that with the speed. Higher the refractive index, lower the speed. Why? N into V is constant. N into V is constant. Higher the N, smaller the V. That is why you see the speed of light in glass is lower. Now, if you compare water and glass, then water has got a lower refractive index. That means the speed is higher. So we say wherever the speed is lower, we say it is more dense. So please remember that. Lower the speed in that medium, more dense the medium. So when we say denser to rarer, that is what we mean. So compared to water, the glass is denser. Compared to water, the glass is denser. That is why when a ray of light goes from water to glass, it bends towards the normal. So like this, we can compare the velocities of light in any two medium, or we can calculate the refractive index of any medium with respect to any other medium. So between any two media, if we consider, the absolute refractive indices of water and glass are known 4 by 3 and 3 by 2. What is the refractive index of water with respect to glass, or air with respect to water, or air with respect to glass? And also comment on what happens to the wavelength when a ray goes from air to water. So we have the N into V is constant. So I can write NGVG, that is refractive index of glass, multiplied with the speed of light in glass is equal to refractive index of water into the speed of light in water. That is constant. So N of glass with respect to water is V in water divided by V by glass. Remember, N21 was V1 by V2. And the ray goes from 1 to 2. That is the terminology that we are using. So NGW is VW by VG. And what is VW by VG from here? VW by VG is NG by NW. So NG is 3 by 2, NW is 4 by 3, so 9.8. That is what we saw last time, 1.125. Now he's asking of water with respect to glass. So NWG will be NW by NG. That is, NW is 4 by 3, NG is 3 by 2, that is only 8 by 9. One observation we can make. NGW into NWG is equal to 1. Now the absolute refractive index of any material is always greater than 1, because that absolute refractive index N is equal to speed of light in air divided by the speed of light in that medium. This is always lower than C, therefore N is always greater than 1. the absolute refractive index of any material. But refractive index of one material with respect to another can be less than 1, as we see in the case of N of water with respect to glass. So all this can be very easily remembered if you just remember this particular one. N21, we wrote it is V1 by V2, that is also N2 by N1. Ray goes from 1 to 2, that is the meaning of N21. N21 is N2 upon N1 or V1 upon V2 because N1 V1 equal to N2 V2. Next is asking what is the refractive index of air with respect to water or air with respect to glass. So N of glass is 3 by 2 and I've written deliberately A here, so we don't write when it is coming from air, then we don't write. So NGA means the ray is going from air to glass, that is known to be 3 by 2. But he's asking of air with respect to glass, that is NAG, from this formula that NGW into NWG is equal to 1. Therefore, NAG will be 1 upon NGA 2 by 3. What is this air with respect to water? N of water with respect to air is basically NW, and NW is 4 by 3. Therefore, N of air with respect to water will be 1 upon NWA, that is 3 by 4. So all of this can be remembered if you just remember this. Don't make a mistake in terms of what is divided by what. N21 is N2 by N1 is equal to V1 by V2. And what does N21 mean? It means ray is going from 1 to 2, not from 2 to 1. What about the wavelength? When a ray goes from air to water, in water the speed decreases. Now the relationship between speed, wavelength and frequency is this, that the speed is equal to frequency times wavelength. Frequency is decided by the source, that doesn't change. So if the speed were to reduce, then the wavelength will also reduce. That is what happens in water when it goes from air into water. All right. Let's talk of Snell's law. The ratio of sine I to sine R is a constant for the given pair of mediums and the color of light. So here we have air glass interface. A source of light is here. A ray of light hits obliquely. Glass is denser than air, so it bends towards the normal. Then at this diffraction, it is going from denser to rarer, so it bends away from the normal. And since these lines are parallel, therefore, incident ray is parallel to the emergent ray. This is the angle of incidence. This is the angle of refraction at the first refraction. At the second refraction, this is the incident ray. So this, what I've written as R is actually angle of incidence. And this is the angle of refraction. But due to the geometry, this line and this line are parallel. So this is R, this is also R. And accordingly, this also will be I. So at the point A, sine of I by sine of R will be equal to N of glass in this case. Now, again, if we write, this is what everybody remembers it as. Snell's law is sine I upon sine R is equal to N. But be very clear, this is NGA, right? This is NGA, sine I by sine R. At the point A, it is NGA. What was N21? Ray was going from 1 to 2. So it is going from air to glass, right? So it makes sense. And NGA is nothing but NG. So that's what. But at the point B, what can we write? At the point B, what do we write? Angle of incidence is actually sine R. It is equal to R. And angle of refraction is I. So sine R by sine I, is that equal to N? Which N? This will be the N of air with respect to glass. It is going from glass to air, right? So that means it will be 1 upon ng. Now, all of this can confuse you. If you just remember Snell's law as sin I by sin r is equal to n, then which n? Therefore, the better way is this. That suppose I say this angle is theta 1, this is a normal. The incident angle is theta 1 and their refracted angle is theta 2. The refractive index of this is n1 and of this is n2. The absolute refractive index. Okay, now sin I by sin r, sin theta 1 by sin theta 2, it is going from medium 1 to medium 2, and this will be equal to n of 2 with respect to 1. And if you just go back to that formula, n21 was n2 by n1, right? n21 was n2 by n1. That's it. So we can write n1 sine theta 1 is equal to n2 sine theta 2. That's it. That's a far better way to remember Snell's law. Then you won't make a mistake. n1, n2 are the absolute refractive indices. Theta 1 and theta 2 are respectively the angle made by the ray with the normal at the point of incidence. That's it. n1 sine theta 1 is equal to n2 sine theta 2. It is a perfect way of remembering. If you just remember sin I by sin r equal to n, then we saw that at the point B there can be confusion. That sin r by sin I is equal to n, or is it 1 by n? Okay. So in the lab, how can we find the refractive index of a material? Very simple. We place that, let's say it's a rectangular glass slab on a sheet of paper. This is the air part, this is the glass part, okay, on a sheet of paper. Then we put 2 pins at an oblique angle and we put our eye this way to observe the refracted ray. So we put 2 pins and after that we remove the slab and we now know the position of the pins. We draw a line with a pencil and another line with a pencil. So this is I, this is R. We don't need to measure this angle with a protractor. What we do is that at this point of incidence, we draw any circle. Then this line and this line that is perpendicular, the radius is R, right? So sine I is equal to this distance, say AB, divided by the radius. And sine R is this distance, let us call it CD, divided by the hypotenuse. Therefore, sin I by sin R will be the absolute refractive index of this glass slab, let us call it N, and for air the absolute refractive index will be 1. So sin I by sin R is AB by CD. That's it. We don't need to measure these angles, we can measure this line AB, just draw a perpendicular line. The ratio AB by CD gives you the refractive index of this material. And only one reading is not sufficient. Take at least 5 readings with different angles of incidences. Let's experiment to find the refractive index in the lab. Now, let me ask you a question. Suppose you are the swimming coach. This is a swimming pool. Your job is to train the children. Your job is also to protect the children. There should be no injury, no drowning. And then you suddenly find that the child over here in the deep end is struggling and is kind of drowning. You see him. You got to rush to him. You should reach him as soon as possible and save him, right? Your task is to reach the child as soon as possible. What route will you take? Will you take the straight line route indicated by option 1? But we know that anybody's running speed on land is far higher than his swimming speed in water for anybody. So here I've given this some data. Coach's running speed on land is 5 meters per second, but in water his swimming speed is much lower. For anybody that is true. So now you have to minimize the time. Will you take the path one, or you say, oh, in path one I have to swim a lot through water, let me reduce the distance that I have to travel in water, so I will go by option 3, where the distance in the water is the least. Or would you take some other in between route like 2? Which one will you take? Think about it. Pause the video and restart the video when you have thought about it and worked out some kind of a solution. Okay, guys, the best path is the second path, not the first, not the third. Such that this point is decided on what basis? You're coming here with some speed V1, this is medium 1, this is medium 2. In medium 2, your speed is lower, so the medium 2 is denser. And then you enter medium 2 at a lower speed V2. Okay, V1, V2. This is the angle of incidence. This is the point of incidence. This is the normal at the point of incidence. This is the angle of incidence. This is the angle of refraction. So this point is chosen such that the sine I upon sine R is the refractive index of this medium 2 with respect to medium 1, right? So sine I by sine R should be equal to speed in air, that is V2, V1. The speed in air is V1 divided by the speed in water, that is V2. And V1 is 5 and V2 is 1. So sin I by sin R is 5. That is the path that will take you from this position to that position in the least time. And this is Snell's law. But actually, all of that comes from the basic principle of Fermat. Fermat's principle of least time. It says that light travels from one point to the other so that it takes the least time to do so. The distance is not the issue. It should take the least time. If you compare option 1 versus option 2, the sheer length of the line for option 1 is smaller than that for option 2. That means the sheer distance of option 2 is greater than the distance in option 1, but the time taken in option 2 is lower. More the distance, more the time is not necessary. The speed is also to be considered, right? Just to give you an example, if I'm driving like this and I need to reach this point, but there are lots of cars in front of me, so I'm going to go very slow to reach this point, right? But if I take a shortcut, a lane like this, then there's no traffic on this road. If I take this route, I'm going to reach this point earlier in lower time, but the distance is more. Doesn't matter. My speed is also greater, right? So the time taken is a function of both speed and distance. The Fermat's principle applies whether light is reflecting or whether light is refracting. It always goes from one point to the other so that it takes the least time to do so. And Snell's law, which is sin I by sin R is equal to the absolute refractive index of this medium, is basically following, or rather, it is basically consistent with Fermat's principle. Beautiful, isn't it? So let us look at some absolute refractive indices. As I said, the speed of light in air is nearly the same as that in vacuum. So for air, it is very close to 1. For various other things I've indicated, for diamond, it is very high. Let's compare water and kerosene. Water is 1.33, kerosene is 1.44. I mentioned earlier, a high refractive index means it is more dense, optically more dense. That means lower speed. High and low speed. Now, interestingly, kerosene, therefore, will be called optically more dense because its refractive index is more than water. Optically more dense, but from the mass perspective, kerosene is lighter than water, so its mass density is lower. An optically denser medium may not have greater mass density. Kerosene has got a lower mass density than water. It floats on water, but it is optically more dense. Therefore, there is no connection between mass density and optical density. The two things are completely different. There's no connection, there's no relationship. What can we conclude from the fact that the absolute refractive index of diamond is 2.42? What is the meaning of this? So, N of diamond is speed in air divided by the speed in diamond. That is the definition of absolute refractive index, and that is given to be 2.42. That means the speed of light in diamond is 1 by 2.42 times the speed of light in air. That is the meaning. Larger the refractive index, you can see, smaller the speed. In fact, N into V is constant. N is the absolute refractive index, V is the speed of light in that medium. That product is equal to C, and that is constant. If N is high, then V is low. That is the meaning of refractive index. So the factors affecting refractive index are, first of all, the medium, its optical density, and this optical density for some medium does have a relationship with temperature as well. Example, hot air has got lower refractive index than cold air. That is not due to mass density. Hot air expands, volume goes up, the density goes down. That is mass density. Yes, that is true. Hot air is less dense from the mass density perspective than cold air. But it's not related here. Hot air still has a lower refractive index than cold air. Then the refractive index also depends on the color of light, which is the frequency of light. You see, the speed of all colors in vacuum is the same, 3 into 10 to the power 8 meters per second. If a ray of light having all the colors enters from vacuum into a certain medium, all the colors will reduce in speed. All colors will reduce in speed. But the reduction is different. Violet slows down much more than red, for instance. The speed of violet color of light in any medium is smaller than the speed of red color of light in that same medium. And if the speed is less, then the refractive index is more. So this is very interesting. N of violet is greater than N of red for any medium other than air. So we'll continue with some more discussion on this topic.